In this video, we'll do part 2 of trigonometric integrals, and this time we're going to focus on the powers and the products of the secant and the tangent, as well as other more general cases. So the story is just not as clean with the secant and the tangent as it was with the sine and cosine. But what does remain the same is that we use the relationships between these functions to anti-differentiate them. We use the derivative relationships, the derivative of tan being secant squared and the derivative of secant being secant tangent. And those derivatives, they're just not as clean as the sine and cos derivatives. So the resulting antiderivatives here just aren't as nicely categorized. We're also going to use the trig identity. It's also a Pythagorean identity like there was for the sine and the cos, that tan squared plus 1 is secant squared. And so I'm going to just show you what the textbook has to say about the integrals of this form, tan to the m, secant to the n. And so there's two sort of cases which do work really nicely, and then there's everything else, right? So some integrals actually are going to work in either way, right? Some will be possible by A and by B, and then others will work in neither way, in which case this is what they say here. For other cases, the guidelines are not clear-cut. You need to use identities, integration by parts, ingenuity, which always strikes fear into the hearts of students. What? I need to be creative? Yeah, you kind of do. So we're going to do examples of each of them here. So example 1 will be of this first part, and that is where the power of secant is even. Example 2 is going to be of part B here, where the power of tangent is odd. And then the last two examples that we'll do are just examples of, well, something else. So let's go through and look at example 1. The power of secant is even. So if the power of secant is even here, right, 4 is an even number, then what do? You pull out a secant squared. So I can write secant to the 4th as secant squared times secant squared. And why would I do that? The same reason that we pulled out powers with the sine and the cosine. You are imagining creating a du. You are imagining creating du as that power that you just pulled out, which means that this is the du that I am hoping to get. And if I am hoping to get secant squared as the du, then the u would have had to have been tangent. So what am I going to do? I'm going to rewrite everything that is left in terms of the tangent, which means that I am using the identity that secant squared x is tan squared x plus 1 to rewrite the secant in terms of the tangent. And then from that point on, it is a simple u sub. Right? It's a simple u sub. So as in the previous video, when you prepare everything correctly using your trig identities and your derivative relationships, then what follows is super easy. It's just a trig sub. So if u is tangent of x, tan squared becomes u squared, tan squared plus 1 becomes u squared plus 1, you expand, you use the power rule, and you revert. So those are always your final steps of any sort of trigonometric integral of this type. All right. Example 2 was when the tangent power is odd. Right? So we just had secant being even, tangent being odd, and it's the same game. It's the same game, except now you pull out secant tangent. You pull out secant tangent, and you're imagining that that is going to be your du, right? And if that is your du, what had to be u? Well, it has to be the secant. So you are going to go ahead and rewrite everything that remains in terms of the secant, right? So the tangent, if you rearrange that identity, the tan squared is secant squared minus 1. So the tan gets rewritten as a secant, the secant stays, and then we do a u sub. Then we do a u sub, right? We just do this u sub, so we get a u, and then it's the same steps, guys. It's the same steps. You expand, you do the power rule, and you revert. So those preliminary steps are what change. Okay, so those are the two cases that work nicely. That was case 1 where the secant is even, case 2 where the tangent is odd. Everything else for secant and tangent is meh, good luck, right? So you need to use identities, maybe some integration by parts, some creativity. So let's look at the next 2 examples to see what might happen there. So in example 3 is delightfully short. What if we had tan squared? Well, if we had tan squared, then we just use that same identity. And if we use that same identity, right, that one. If we use that same identity, then boom, it's done. Right? The antiderivative of secant squared is tan. Antiderivative of 1 is x, and then plus c. So in certain cases, it's super easy. Now, what about secant cubed? Well, that one is not so easy. So this one, integration by parts. How do you know? Well, you kind of don't. You do examples and you remember what you've seen, and then you try different things, and well, that's what it is. That's what it is, guys. So IBP, integration by parts. Integration by parts. And this procedure is actually the exact same procedure that we did when we did the reduction formula for secant to the n of x dx. It's the same procedure. It's the same procedure that we did there. So it might feel familiar to you. And so what we did is we used a law of exponents, and we took the secant cubed and split it up as the secant times the secant squared. Then we did IBP. We remember when you do IBP, you have to decide which one you are going to anti-differentiate first, and then make your choice for dv according to that. So secant squared, much easier to anti-differentiate. We'll get v as tan x, which leaves u as secant x, so du is secant tangent. The antiderivative, or the integration by parts formula, is u times v, right? So secant x times tan x minus the integral of v du. So this v du here, if I put v and du together, v and du together, I get secant x, and these two tangents multiply to give me tan squared. I use that same trig identity, the same trig identity that we've used a couple times now. Distribute in the secant, and so we get secant cubed minus secant of x. Distribute the integral and the negative sign, so we get minus secant cubed of x plus secant of x. And ooh, look at that. Boomerang. That integral is the same integral that we started with. So we're going to boomerang it to the other side. I had one of them here, and I'm going to add another one when I boomerang it over. So 1 plus 1 of those integrals is 2. So 2 times the integral of secant cubed of x dx. Well, this tangent, secant tangent just gets rewritten, and the integral of secant that we did previously, and that is one that you are supposed to memorize. So the antiderivative of secant, ln of the absolute value of secant plus tangent plus c, divide both sides by 2, and there you have it. All right, so a little ingenuity and creativity, depending on the cases here that you get when you do not have the lovely first 2 cases as described in the textbook. So let's just look at a couple other non-standard trigonometric integrals, and then there's no hard and fast rules except use trig identities, use derivative rules, and just try and figure something out. And so we're going to do 2 examples of this kind here with non-standard integrals, and that will be it for this video. So let's look at what happens if we get the antiderivative of this. 1 minus tan squared over secant squared dx. This is algebraic techniques that we've done before. We are going to split the denominator. If we split the denominator, you get 1 over secant squared minus tan squared over secant squared. Now you're going to use some trig identities, right? 1 over secant squared is cos squared. You are going to rewrite tan squared as sine squared over cos squared. Divide by secant squared is like multiplying by cos squared. The cos squareds cancel. You're going to have then cos squared minus sine squared, which you might recognize as an identity from high school. And if you do, you can just jump to this step. If you don't, well, that's okay. You can rewrite this using the half angles that we did earlier. If you use the half angles here and then clean up, right, this 1/2, you've got 1/2 that's going to cancel with that 1/2, and then you've got 1/2 of this minus minus gives you another, right? You get 1/2 cos 2x minus 1/2 cos 2x, and those will add up together to give you cos of 2x. Mini sub, you've got a 2 here, so you get a 1 over 2 outside, and antiderivative of cos sine 2x plus c. Right, so that is a non-standard trig integral, non-standard example using just all of your trig knowledge and algebra knowledge that you have accumulated. One more of these is going to be another integration by parts. What if you have a product here, a product of two functions that are not, they don't have the same argument. This is x, this is 3x. There are other identities. There are other ways of doing this, but the way that I am going to choose to do it is another integration by parts. So I'm going to set up my integration by parts here, and I'm going to let u be the cos of 3x. So du is minus 3 sine 3x. dv is sine, v is minus cos. So here is my uv minus the integral of v du. So that's actually minus, 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 right? Minus the integral of v du. Those two minuses cancel, but I'm left with one minus. The 3 comes outside, and then I've got 3 cos x sine 3x, which means I'm going to need another integration by parts. And here's my big suggestion. Continue down the same stream, right? This was u. Keep it in the u stream. Don't make this the v now. Don't switch over and make the v or the dv sine of 3x, right? Don't go ahead and make this the dv. If you do, everything is going to cancel out, and you will prove without the shadow of a doubt that 0 equals 0. Which is true, but not useful to your integration. So once you have chosen the function as your u, continue down. And as far as choice, it doesn't matter. At the initial choice doesn't matter. But once you've made that choice, stick with it. So you reapply integration by parts, right? Here's one time, here's the second time. So you reapply integration by parts. You're going to get this. Be sure to open a bracket so that your constant outside can then be multiplied through afterwards. You will notice that you get the same antiderivative here that is going to boomerang onto the other side. Now we've got to be careful. We have one of those integrals on this side to start with, right? We had one of them. We are minusing 9 of them when we boomerang this over, which means we get minus 8 times the original integral is whatever is left on the other side. Divide by minus 8, and you get this as your answer. So those are two non-standard. I can't show you all the non-standard because there's just too many of them. But, right, so you've seen the patterns, the nice patterns, and then you've seen ones where you do have to be a little bit more creative and try different techniques that we have seen before.